Welcome to the video lecture on the alternating series test. Let's recall that the integral test, direct comparison test, and limit comparison test all require that the terms of the series are positive. However, many series such as sine of n over n squared, negative 1 to the n times 1 over n, and negative 1 to the n times n over n plus 1 do not have all positive terms and thus cannot be investigated using the above mentioned tests. So we need a test that deals with series whose terms alternate in sign, and this is called the alternating series test. So here's what it says. First, we're going to assume that a sub n is greater than 0. Then the alternating series negative 1 to the n times a sub n, or negative 1 to the n plus 1 times a sub n converge if the following two conditions are met. So a sub n plus 1 is less than or equal to a sub n for every n. So the terms, these a sub n terms, need to be getting smaller. And the limit as n goes to infinity of a sub n has to equal to 0. Remember that if your limit of a sub n does not equal to 0 right from the start, you know that your series must diverge by the nth term test. So this first example, we've got an alternating series because we have this negative 1 to the n times 1 over ln of n. So we're going to see if our two conditions are met. So let's start with the limit right away, since if that fails, then we can just stop and we'll know that we have a divergent series. So let's check the limit as n goes to infinity of just this piece here, the part that does not have the alternating sign, so 1 over ln of n. Now as n goes to infinity, ln of infinity is also infinite, so this is acting like 1 over infinity, which does go to 0. So far, because that limit is 0, we can't conclude convergence or divergence. So let's see if we can verify our second condition. We need to show that a sub n plus 1 is less than or equal to a sub n for every n. Well, we know that n plus 1 is greater than or equal to n. Therefore, the ln of n plus 1 is greater than or equal to the ln of n. But if we take the reciprocals, then this inequality flips around. And the reason why is because the denominator on the left side is bigger, which makes the fraction get smaller. So this relationship that a sub n plus 1 is less than or equal to a sub n is definitely true for every n. So our two conditions are met for the alternating series test. So this shows by the alternating series test that our series converges. So if we look at the next example, we've got negative 1 to the n plus 1 times n over n squared plus 1. So it's an alternating series, so the very first thing I'm going to check is that limit. So let's take a look at the limit as n goes to infinity of just this n over n squared plus 1. Now n over n squared, that's what's dominating here. So when I reduce that, an n over an n squared is going to be acting like a 1 over n. And as n gets big, this is going to act like 1 over infinity, which is going to go to 0. So far I can't conclude anything yet, but I do have some progress towards those two conditions for the alternating series test. So now we go ahead and we want to show that a sub n plus 1 is less than or equal to a sub n for all n. Now in this particular problem, it's not as simple as the last one where you can just look at the two fractions and see that this inequality is true. So one other way that we can show that this relationship is being held is to show that this function up here is decreasing. So what I'm going to do is I'm going to call it f of x and let f of x be x over x squared plus 1. And if this function f is decreasing, then its derivative would be negative. So I'm going to take a look at the derivative, and I'm just going to use my quotient rule. So the derivative of the bottom times the derivative of the top, low d high, minus high d low, the derivative of the bottom would be 2x over the bottom squared. So when I simplify this, this is going to become x squared plus 1 minus 2x squared over x squared plus 1 quantity squared, and this becomes 1 minus x squared over x squared plus 1 quantity squared. Now remember, we're looking at n's, or in this case x's, that start at 1 and go to infinity. So if x is 1, then this is going to be 0. But for all the x's after 1, 2, 3, 4, 5, and so forth, this numerator is definitely going to be negative, and the denominator is always positive. So this will be less than 0 for all x's greater than 1. Remember that it's okay if you have a finite number of terms at the beginning that do not satisfy your conditions. The series will still be convergent or divergent if we can show that it's convergent or divergent for the rest of the terms beyond those first initial finite terms where the conditions aren't satisfied. So this is decreasing for x is greater than 1. So our two conditions, the limit and the decreasing, are met. So by the alternating series test, this series converges. So let's take a look at the next example. We have the limit of -1 to the n plus 1 of n cubed over n cubed plus 6. So this is an alternating series, so if I look at that limit right away, the limit as n goes to infinity of n cubed over n cubed plus 6, what dominates is this n cubed over n cubed, which is just going to reduce to a 1. And the limit of 1 stays 1, and this is not 0. So what we can conclude, since this is not 0, is right away this must diverge by the nth term test. And that test says again that if your limit as n goes to infinity of a sub n is not 0, then your series cannot converge. It has to diverge. If the limit is 0, then we can't conclude one way or the other. So this time we're done. We already know it diverges, and we can move on. So if we look at this next example, again another alternating series. So I'm going to use my alternating series test. I'm going to take a look at my limit as n goes to infinity of this 1 over n factorial. Infinity factorial is going to stay infinite, and 1 over infinity is definitely 0. Okay, so that condition is met. So now we want to try and show that a sub n plus 1 is less than or equal to a sub n for all n. Well, we know that n plus 1 factorial is greater than or equal to n factorial, since n plus 1 is bigger than n. So in the reciprocal, 1 over n plus 1 factorial must be smaller than or equal to 1 over n factorial. Since the denominator here is bigger, that makes the fraction smaller. So we've just shown this relationship is true for all n, and that means by the alternating series test, the series converges. So this alternating series test is actually a pretty nice nice test to use, because the conditions are fairly simple and straightforward to show most of the time. Now let's take a look at this one. This one doesn't look obviously like an alternating series because you don't see that -1 to the n or -1 to the n plus 1. But if we expand it out a little bit, let's see what some of the terms look like. So if n is 1, then this would just be cosine of pi, which is -1. If n is 2, cosine of 2 pi is +1. If n is 3, cosine of 3 pi is back to -1. If n is 4, we have cosine of 4 pi, which is back to +1. So this is technically an alternating series, and this is what it would look like. So does this converge? No, it doesn't, and you can say that by a couple of different options. One thing you could say is that the limit as n goes to infinity of this cosine of n pi, that's obviously not going to 0 because these terms are either 1s or -1s. So this limit is not 0 because they oscillate between -1 and +1. And you need that nth term to go to 0, and these are not. So it definitely will diverge by the nth term test. You can also see by looking at partial sums, the first partial sum would be -1, second partial sum would be 0, the third partial sum would be -1, the fourth partial sum would be 0. So those nth partial sums are oscillating between 0 and -1, so they don't converge as well, which means the series cannot converge. Okay, if we look at this next example again, we don't see that -1 to the n at all. But if we expand it out, let's see what some of these terms look like to see if this really is an alternating series. So if n is 1, this first fraction is just going to be 1, and cosine of pi is negative. So this will be just negative 1. If n is 2, this fraction becomes a half, and cosine of 2 pi is positive 1. So this will be positive 1 half. If n is 3, we get a third, and cosine of 3 pi is negative, so this will be negative 1/3. If n is 4, we get 1/4 times cosine of 4 pi, which is positive 1, so this will be back to positive 1/4. So these are just our normal fractions that we see in our harmonic series. However, they're alternating, so this is called the alternating harmonic. So we know that the harmonic series diverges, but what about the alternating harmonic? So let's look at our alternating series test applied to this series. If we look at the limit as n goes to infinity of this nth term, the nth term you can see is either going to be positive or negative 1 over n. And as n gets really, really big, that's definitely going to go to 0. So this piece here is either going to be plus or minus 1, and this piece is going to be 1 over infinity, which is going to go to 0. So yes, this limit will go to 0. These terms are getting smaller and smaller. So that condition is satisfied for the alternating series test. The second condition that we need to show is that a sub n plus 1 is less than or equal to a sub n. And again, you can see that from here because these fractions are either going to be 1 over n or 1 over n plus 1, ignoring the pluses and the minuses. When we're doing the alternating series test, we ignore the alternating piece when we're checking these conditions. So the fraction 1 over n plus 1 has a bigger denominator, so it's a smaller fraction. So this is met for every n, and therefore this condition is met as well. So this series, this alternating harmonic series, does converge by the alternating series test. So the regular harmonic diverges, but the alternating harmonic will converge. Now there is nothing in the statement of the alternating series test that refers to what the series converges to. However, there is a theorem that deals with this issue. It's called the alternating series remainder. If a convergent alternating series satisfies the condition that a sub n plus 1 is less than or a sub n for all n, so the terms in the sequence are decreasing, then the absolute value of the remainder, r sub n, involved in approximating the true sum by the nth partial sum is less than or equal to the first neglected term. So the difference between the true sum and the approximation will be less than or equal to the very next term that you are disregarding or that you're leaving off. So if we look at the nth partial sum as an approximation to our sum, then the nth plus 1 term will give us sort of an error bound on how accurate our approximation is to the true sum. So let's look at a proof of this. It's already typed up here. Suppose that we have the sum from 1 to infinity of negative 1 to the n minus 1 times a sub n, and we know that this is a convergent sum. Then if we delete the first n terms, it will still be convergent. We're allowed to disregard a finite number of terms at the beginning, and the series will still be convergent. So that means the remainder, r sub n, which is the true sum minus the first n terms, will be convergent as well. So if we write out what that would look like, r sub n is equal to the full sum minus the nth partial sum, which is going to be the sum starting at the nth plus 1 term and going to infinity. So the true sum is a sub 1 plus a sub 2 plus a sub 3 all the way to infinity, and s sub n is just a sub 1 through a sub n. So if I subtract off those first n terms, then I'm just looking at the nth plus 1 term on. That's what this is saying. Now if we expand that out, that's going to look like negative 1 to the big N times a sub n plus 1, plus negative 1 to the n plus 1 times a sub n plus 2, and so on to infinity. Now notice that each of these terms here has a negative 1 raised to an n in it, so let's factor that out. So if I pull out that negative 1 to the n, I'll be left with a positive a sub n plus 1, a minus a sub n plus 2, a positive a sub n plus 3, a negative a sub n plus 4, and so forth. So these terms inside here alternate signs. Now if I take the absolute value of our remainder, that's going to cancel out this negative 1 on the outside and make it turn positive. So we're just going to get those alternate terms right here. Now I'm going to group these. I'm going to leave a sub n plus 1 as it is, and I'm going to factor out of these two terms a negative, which makes the a sub n plus 2 positive and the a sub n plus 3 becomes negative, so that when I redistribute the negative across, I would get back what I started with. Then I'm going to take these two terms, factor out a negative, so the a sub n plus 4 is positive and the a sub n plus 5 is negative. And likewise for the next pair and the next pair and so forth. Now what do we know about these terms? We know that a sub n plus 1 is smaller than or equal to a sub n. So this term is smaller than this term, which means when I subtract, this is going to be a positive difference. I'm subtracting something that's smaller, so I'll still have a positive answer left over. Likewise here, this term is smaller than this one, so when I subtract it off, this will be positive. This is smaller than this, so when I subtract, this result will be positive. And what are we doing with these? Well, we're starting with a sub n, and we're subtracting a positive amount, subtracting a positive amount, subtracting a positive amount. So all that's going to do is make this get smaller. So in terms of a bound, we could say that this remainder is definitely equal to a sub n plus 1 or less than that if these differences are indeed positive. If they're 0, if all of these were 0, then I would just get a sub n plus 1. But if any one of these differences is something positive, then that's going to make this get smaller. So the remainder is bounded by that a sub n plus 1. It can't be any bigger than that. Okay? So this gives us a way of determining how to best approximate a sum within a certain error bound. So for example, if I want to approximate the sum of the convergence series negative 1 to the n plus 1 times 1 over 2n factorial with an error less than 0.001, that means I want my remainder to be less than or equal to the first term that is going to be less than this 0.001. So what I want to do is I want to find the first term that is less than this bound 0.001, this error that I'm looking for. And once I know the first term that is less than that, then I can use all the terms prior to that term to approximate my sum, and I'll be guaranteed that the error in approximating my sum will be less than this 0.001. So let's just look at a generic term. I'm going to ignore the alternating piece and just use this a sub n. So I want to know, when is this generic term first going to be less than 0.001? So if I multiply both sides by 2n quantity factorial and then divide by 0.001, 1 divided by 0.001 is just 1,000. So we're looking to see when will 2n factorial be greater than 1,000. And you can just use your calculator for that. If we pull up the calculator, I'm typing into my y1 this 2x factorial, and I'm just going to look at a table to see when does 2x factorial first become bigger than 1,000. And you can see that at 3 it's 720, which isn't quite 1,000, but at 4 we get 40,320. So this is going to first hit something larger than 1,000 when I have an x of 4. So that means this is true. This happens when I use an n equal to 4. Okay, so what does that mean for me? Well, it means that I can approximate the sum using all the terms prior to this. This n equals to 4 is the first neglected term. So we get to use all the way up to n equals to 3. So we're going to approximate the sum with our third partial sum, which would be the very first term. So if I look at my sum up here, when n is 1, this is 1 over 2 factorial, which is just a half. And when n is 1 for this power, negative 1 squared is positive. So when n is 1, this is just 1 over 2 factorial. When n is 2, this becomes negative, and I get 1 over 4 factorial, and it's a minus. And when n is 3, this becomes 1 over 6 factorial, and 3 plus 1 is 4, which is even, so this goes back to being positive. So the third partial sum, or the first 3 terms added up, would give me this, and in terms of a fraction, that's 91 over 720, which is approximately 0.126. So we can be assured that the true sum of this convergent series is equal to 0.126 within an error of 0.001. We've guaranteed that the error by making this approximation is less than 0.001. Let's try another example. Find the number of terms to include in the sum of the series negative 1 to the n times 1 over n times 1/2 to the n, so that the remainder is less than 0.005. So just like before, what we're really looking for here is going to be the first term that is less than 0.005, because that's what our remainder actually is. So our generic term would be this part right here. And we want to know when that first hits 0.0005. So again, I'm going to pull up my calculator, and I have it typed in. There's my generic term, 1 over x times 1/2 raised to the x. And if I look at my table, we're looking for which of these terms first gets smaller than 0.0005. So far none of these are smaller than 0.0005. So I'm going to have to scroll down. And 4.9 times 10 to the negative 4 would be 0.00049, which is indeed less than 0.005. So when n is equal to 8, this will be less than 0.0005. So when n equals to 8, we get that a sub n is 0.00049, which is less than this error that we're looking for. So that means we can use the first 7 terms to approximate our sum within an error of 0.0005. And this one doesn't actually ask us to find what the sum is, it just wants us to find the number of terms. So we can use 7 terms here. The first 7 terms will give us a fairly accurate approximation to the sum within an error of 0.0005. Okay, now we're going to talk about something a little different at this point. We're going to talk about a series that is considered absolutely convergent and conditionally convergent. So the definition is that a series a sub n is absolutely convergent if the series, the absolute value of a sub n, is convergent. So when you're looking for absolute convergence, you're looking at the absolute value of this nth term. Now, if your sum already has all positive terms, then absolute convergence is going to be the same, and it's going to be automatic. So a sub n would be the same as the absolute value of a sub n if all your terms are already positive. So all convergent series having only positive terms are absolutely convergent automatically. Now we say that a series a sub n is conditionally convergent if the series a sub n is convergent, but the absolute value of a sub n is divergent. Okay, and an example of that would be our alternating harmonic series. We showed earlier that when you have that alternating piece in there, it does become convergent by the alternating series test, but in the absolute value, yeah, the alternating harmonic just becomes the harmonic series, which is divergent. So let's determine whether each of the following is absolutely convergent or conditionally convergent or just plain old divergent. So the first thing we're going to do is to determine absolute convergence is look at the absolute value. So if I took the absolute value of this, all that does is it strips away that alternating piece, that -1 to the n, and just makes this become 1 over n squared. Now, is that a convergent series? Yes, this converges because it's a p series with p equal to 2, which is bigger than 1. So since in absolute value it converged, that means the alternating series will also converge, and we can say that this absolutely converges. Now if we look at the absolute value of this next sequence, -1 to the n times 1 over n, in absolute value, that -1 to the n goes away, and this just becomes 1 over n. And that's the harmonic series, so it diverges. It's a p series with p equal to 1. So if we want to show that this does converge, if it's going to, then we could pull back, erase these absolute values. We know it's not going to be absolutely convergent, so this shows that it's not absolutely convergent, but it could be conditionally convergent if we disregard the absolute values. And to show that this is convergent, we used that alternating series test. So if we look at the limit as n goes to infinity of just this a sub n, that is going to go to 1 over infinity, which goes to 0. And we know that 1 over n plus 1 is indeed smaller than 1 over n, since this denominator is bigger, so this fraction is smaller. So this is true for all n. And those are the two conditions that we need for the alternating series test. So that shows that this does converge by the alternating series test. It didn't converge absolutely, but it does converge conditionally. So this converges conditionally. And again, this was called the alternating harmonic series. So with that -1 to the n in there, it does make it converge. But without it, it will diverge. If we look at this next example, we have this alternating series. So in absolute value, this would just become the series from 1 to infinity of n over n plus 2. Now, right off the bat, you should start to be looking for this before you even jump into things. You want to notice that the limit as n goes to infinity of that nth term, whether you look at the absolute value or the original, this limit of this a sub n goes to n over n, which goes to 1, which is not 0. So the fact that that nth term is not going to 0 means that this has to diverge by the nth term test. So it's not convergent absolutely or conditionally. Okay, how about this next example? We've got -1 to the n times 3 to the n over 2 to the n plus 1. So in absolute value, this would look like the series from 1 to infinity of 3 to the n over 2 to the n plus 1. And again, if you look at that limit, as n goes to infinity of that nth term, you might want to rewrite that denominator a little bit and break up that 2 to the n plus 1 and think of this as 3 to the n over 2 to the n times 2 to the first, or just a 2. And what I would recommend doing here is thinking of that 2 in the bottom as like a 1/2, and it's being multiplied by this 3 over 2, and both of those are being raised to the n. Now that is a geometric type series, right? And your ratio r is this 3/2. So think about what that's going to do as n gets really, really big. If your r is bigger than 1, like 2 to the n, 3 to the n, 4 to the n, 1.5 to the n, what happens as n goes to infinity? As this power gets big, since this base is bigger than 1, this is going to continue to blow up. Okay, so 2 to the infinity is still infinite. 3 to the infinity is still infinite. 1.5 to the infinity is still infinite. So this is not 0, which means this must diverge by that nth term test. How about n over 5 plus 3n squared? If we look at that limit right away of n over 5 plus 3n squared, since we've been doing a lot of these nth term tests, this is being dominated by an n on top and a 3n squared on the bottom, which is acting like just a 1 over 3n. And as n gets big, that means the fraction gets small. So this does go to 0. So we can't conclude one thing or the other. We can't conclude convergence or divergence. So let's back up and let's look at our absolute value and see if this is absolutely convergent. Because if it's absolutely convergent, then we can stop and we'll be done automatically. So the absolute value would just be n over 5 plus 3n squared. Now when you look at that, this is acting like an n on top and an n squared on the bottom, so it's acting like a 1 over n. So hopefully by now your instinct is telling you that we could probably compare this to the divergent series 1 over n. So in order to show that, you could either do a direct comparison test, which would probably be difficult to do that term by term comparison, or you could do a limit comparison test. So the limit comparison test says to look at the limit as n goes to infinity of your unknown series over your known series. And if I multiply by the reciprocal, then this becomes the limit as n goes to infinity of n squared over 5 plus 3n squared, and that is being dominated by n squared over n squared, which is a third, which unfortunately is greater than 0, so that means that whatever this series does, which we know that it diverges because it's harmonic, this series does as well. So this shows us by the limit comparison test that the absolute value of our given sequence diverges. Therefore, it's not absolutely convergent. Remember, we got this series by taking the absolute value. So all we've proven so far is that it's not absolutely convergent. It could still be conditionally convergent. So to determine conditional convergence, we take away these absolute values and we go back to this alternating series. And we usually at this point would pull out our alternating series test. We've actually already shown the first condition required for the alternating series test. The second condition we would have to show is that a sub n plus 1 is less than or equal to a sub n for all n. Now that again would be hard to show term by term as being true for this particular function because it's kind of messy. So an alternative is to call this function f of x and call it x over 5 plus 3x squared. And this inequality right here is the same as saying that your sequence is decreasing or saying that this function decreases so that it has a negative derivative. So let's look at the derivative. The bottom times the derivative of the top, which is 1, minus the top times the derivative of the bottom, which is 6x, over the bottom squared. So this is going to be 5 plus 3x squared minus 6x squared, which is negative 3x squared plus 5. So if x is 1, this will be positive, but if x is 2, then this becomes negative if x is 3, this is negative if x is 4, this is negative. So this will be negative as long as we're looking at x is bigger than 1. So it is decreasing, except for the very first term, which we can disregard. And that means we've satisfied our second condition that we needed for the alternating series test. So by the alternating series test, this converges, which means that we are conditionally convergent. We were only able to get convergence when we threw in that alternating piece. Now we have theorems to deal with infinite series which have all positive terms, and with infinite series which have terms that are alternating positive and negative, but nothing to deal with series that are randomly positive and negative, such as sine of n over n cubed. This series, that sine of n, alternates back and forth between positive and negatives, but not at a regular basis. It's not the first one's positive, the second one's negative, the third one's positive, the fourth one's negative. It doesn't do that. It's positive for a while, then it switches to negative when you get to quadrant 3, and then back to positive again when you're back to quadrant 1, and so forth. So this is positive and negative, but not in a pattern. So the following theorem can be used when you have a series like this. It's called the absolute convergence theorem. And it says that if the absolute value of your series converges, then the original series converges. Okay, so if you can prove absolute convergence, then you can show that that means that the original series with that alternating piece in there must converge as well. So here's the proof. First, what we're going to assume is that the absolute value of our sequence does converge, and we're going to try to prove that that means that the original series does converge, the one that has the positive and the negative terms. Now the way we're going to prove this is we're actually going to first show that the sum of a sub n plus the absolute value of a sub n converges. So here's how we show that. We have the fact that a sub n plus the absolute value of a sub n must be less than or equal to 2 times the absolute value of a sub n for all n. And that's because these a sub n's, remember, are positive and negative. So a sub n plus the absolute value of a sub n is going to be smaller than 2 times the absolute value, because some of these a sub n's are going to be negative, which will subtract away from this. So this left side will be smaller occasionally than this right hand side. So that means that this series that we have on the left here, which is the smaller series, must converge by the direct comparison test, since we know that this converges since it's just a constant times a convergent series. We already assumed that the absolute value series converged, so 2 times it will still converge as well. So by the comparison test, the smaller series must converge if the bigger series converges. Okay, so now we've just proven that a sub n plus the absolute value of a sub n converges. Now we're going to use that, and we're going to be a little bit clever. We're going to show, or just realize, that a sub n is really just the sum of a sub n plus the absolute value of a sub n minus the absolute value of a sub n. I'm adding in a fancy version of 0 right here. Now I'm going to split this up into 2 series. I'm going to take the sum of a sub n plus absolute value of a sub n, and then I'm going to subtract from it the absolute value of a sub n. So I've got one series here and one series here. Now we just showed that this converged by that direct comparison test, and we already know that this one converges because that was the assumption we were making. So if you have 2 convergent series, then their difference converges as well. So therefore, the original sum of a sub n, which was equal to all of this stuff, must converge also. Okay? All right. Now how do you use this? Well, sometimes you can see that it will be fairly easy to show that an absolute value series converges. If you can do this, then you can conclude that the original series also converges. So just by looking at this, this would be hard to show convergence initially because we can't use the comparison test limit comparison test or integral test because these are not always positive terms. And we can't use the alternating series test because it doesn't look like -1 to the n times an a sub n. These are only sometimes positive and sometimes negative. There's not a pattern to it. So since we can't use any of these tests, we would potentially be stuck to show whether or not this converges or diverges. So what we can notice is that if we look at the absolute value of this series instead, that would be the same as looking at the absolute value of sine of n over n squared. And n squared is already positive, so it doesn't even need absolute values. And what we know about sine of n is, since it's a trig function, we know that in absolute value, sine is always between 0 and 1 for every n. So then if I take this inequality here and I divide every term by that positive term n squared, so I'm dividing 0 by n squared, sine of n over n squared, and 1 over n squared, we know that this converges because it's a piece series and it's bigger than this one. So if the bigger series converges, that forces the smaller series to converge as well by our direct comparison test. So that's the proof that this converges by that comparison test with our piece series. So that showed that the absolute value of this series did converge, which means it converges absolutely, and therefore by our absolute convergence theorem, that means the original series without the absolute value must converge as well. So sometimes the only way to show convergence is to look at the absolute value and then show that you have absolute convergence, therefore the original series converges as well. So let's determine whether each of the following is convergent or divergent. So this doesn't look like your typical alternating series. Let's write out some of the terms. If n is 1, this just becomes 1 over 1. 2 times 1 is 2, 2 minus 1 is 1, so this is sine of pi over 2, which is a positive 1. So we just get 1 times 1 for that first term. When n is 2, we're going to get a 1/2, but we'll get 4 minus 1, or 3 pi over 2, and sine of 3 pi over 2 is negative. When n is 3, we'll get a third. 2 times 3 is 6, 6 minus 1 is 5, 5 pi over 2 is the same as positive pi over 2, so that's positive again. So this is that alternating harmonic again. Just doesn't look like it in this particular form, but when you expand it out, you'll see that it is this alternating harmonic series. And we've already proven today that that series converges. So that means that we have a convergent series. So this must converge as well. Now it's not absolutely convergent because in the absolute value we would lose all these minus signs and we would get the regular harmonic series. So it's not absolutely convergent, it's actually just conditionally convergent. Okay, now if we look at the next example here, we have 1 minus cosine n over n squared. So let's write out what some of these terms would look like. When n is 1, we would just get 1 minus cosine 1 over 1 squared. Cosine of 1 is just some decimal. I don't know what it is. You could look it up on your calculator. If n is 2, this is going to be 1 minus cosine 2 over 2 squared, or 4. If n is 3, this will be 1 minus cosine 3 over 3 squared, or 9, and so forth. And again, cosine 1, cosine 2, cosine 3, those are going to be just different decimals that we don't necessarily know what they are off the top of our head. Some of these eventually will become values that could potentially make these signs alternate. Okay? What we can notice though, since we've got a trig function involved, a lot of times if you look at the absolute value of this and look at its absolute convergence, you can show convergence overall. So let's look at the absolute value of this series. The denominator is already positive automatically because of that n squared. So let's consider the size in absolute value of this numerator 1 minus cosine n. You know that the smallest that cosine can get is going to be a 0, and a negative 1 without that absolute value in there. So if cosine was negative 1, then this would become 1 minus a negative 1, which is 2. So the biggest this is going to get is 2. If n is positive 1, then we'd get 1 minus 1, which goes to 0. So that's the smallest this is going to get in absolute value. This can't ever become negative since it's in an absolute value. So our inequality relationship here is that 1 minus cosine of n in absolute value is bounded between 0 and 2. So if we take all of these pieces and we divide them by n squared, which is a positive, so it's not going to flip any of the inequalities around, we know that this converges because it's just a constant 2 times a convergent piece series. And a constant times a convergent piece series, or any kind of convergent series, will still be convergent. So it's convergent, and it's the bigger series. So if the bigger series converges, that forces the smaller series to converge as well. So by the direct comparison test, that means the absolute value of 1 minus cosine n over n squared must converge as well. And if it converges in absolute value, then that means it's absolutely convergent. And by the absolute convergence theorem, that means the original series without the absolute value must converge as well. So absolute convergence is a stronger condition. If you can show that you're absolutely convergent, then you'll definitely converge if you throw in that alternating piece as well. Okay, let's try something similar on this bottom example here. We know that cosine of n in absolute value, if we look at the absolute value of this, is bounded by, it's not going to get any smaller than 0, and it's not going to get any bigger than 1. So if I divide by an n cubed, which is going to be positive since n is positive, then we know that this series here converges because it's a p series with p equal to 3, and it's bigger than this series here. So again, by the direct comparison test, the smaller series, which is our absolute value of cosine of n over n cubed, must converge. And if you converge an absolute value, then that means you're absolutely convergent. So by the absolute convergence theorem, that implies that the original sum without the absolute value must converge as well. So what's the importance of absolute convergence? Well, for one, it's sometimes the only way to show that a series such as sine of n over n squared converges. You can only show that this converges by looking at its absolute value first. Otherwise, we wouldn't have any test that would apply to this. Another thing to note is that if a series is absolutely convergent with the sum of s, then any rearrangement of the terms must also converge to s. However, if a series is conditionally convergent with the sum of s, a rearrangement of the terms can make the series converge to any real number, or you can make the series diverge, or you can make the series oscillate. So strange things can happen if you only have a conditionally convergent series. So absolute convergence is a stronger statement. So in an illustration of this last point, let's take a look at that alternating harmonic series, the negative 1 to the n of 1 over n. This we've already proven today is conditionally convergent, and it can be shown to converge to the ln of 2. So we're going to assume that this sum is equal to the ln of 2. So if n is 1, this would be negative 1 plus a half minus a third plus a fourth minus a fifth, and so on. So if we take a look at that and rearrange some of these terms a little bit, I'm going to take the -1 plus the 1/2 and sort of group them together. And then I'm going to put the 1/4 right in between, and I'm going to group together the -1/3 and the +1/6 that would come over here. And then I'm going to follow that with my 1/8, which will be positive. And then I'm going to follow this by my -1/5 minus my, or plus my 1/10. And then I'm going to have my +1/12, and so on. So every term is accounted for. I'm just kind of reordering them. So here's my 1, my 1/2, my 1/3, my 1/4, my 1/5, my 1/6. The 1/7 would come over here. The 1/8, the 1/9 would come a little later. So every term is actually going to be used. I'm just adding them in a different order. And addition is commutative, so you should be able to do that, right? Now, by reordering them and regrouping them the way that I have, -1 plus 1/2 is the same as -1/2 plus 1/4. -1/3 plus 1/6 is equal to -1/6 plus 1/8. -1/5 plus 1/10 is -1/10 plus 1/12, and so on. And if you notice that each of these terms is divisible by a -1/2, let me go ahead and pull that -1/2 out. So I'll be left with a 1. Actually, let's leave the negative in. I'm going to leave the negative in there. We'll get a -1. We'll get a +1/2. We'll get a -1/3. We'll get a +1/4, a -1/5, a +1/6, and so on. So if I leave that one, if I pull that 1/2 out, look at what we ended up with here. The exact same sum that we started with, which we said was equal to the ln of 2. But I factored out a 1/2 to get that. So that means this sum, which we are supposed to know is equal to ln of 2, is also equal to 1/2 of ln of 2. So by rearranging the terms, and regrouping them in a clever way, we got half of the original sum. So that's that sort of odd behavior that you get when you're dealing with a conditionally convergent sum. Any kind of rearrangement can make the series do strange things. You can get it to converge to any real number, you can make it diverge, or you can make the series also oscillate. So strange things can happen when you're dealing with these conditionally convergent series. All right, that concludes our video lecture on the alternating series test. Good luck.